Hello students, in today's class we will be studying about the bonding in benzene and pyrrole. Both benzene and pyrrole are aromatic structures. We'll start off with benzene, and we have seen the different kinds of bonds which are present in benzene as well. Let me just make the structure of benzene. Benzene is nothing but 6 carbons which are attached or joined to each other, and this is how they look. And these are the double bonds which are there as a part of it. And then you have the hydrogens attached to them as well. This is how benzene looks like. It is cyclic in nature. It is conjugated, that means it has alternate pi bond, sigma bond, pi bond, sigma bond, and so on. And it is planar. And if you see, the number of hydrogens are low. If you see the molecular formula of benzene, it has 6 carbons, 1, 2, 3, 4, 5, 6. So it becomes C6. And the number of hydrogens are also 6. 1, 2, 3, 4, 5, 6. It becomes C6H6. So because of the low hydrogen to carbon ratio in aromatic compounds, that is the H to the C ratio in aromatic alkane. Always remember that H to the C ratios in alkanes will be greater than 2. But since this is not an alkane, it's benzene, it is alkene. It's an aromatic alkene. And because of that, it will not be greater than 2. Chemists expected the structural formula will contain larger number of double and triple bonds. So now what happened was that in olden times, people didn't actually know the structure. People didn't know how a particular compound will look like. So they started finding out the molecular formula of different things. They found out the molecular formula of alkanes, the molecular formula of alkenes, the molecular formula of alkynes. So when they found out the molecular formula, in the molecular formula, what is the molecular formula? You just count the number of atoms of a particular element. That is all. So now molecular formula, you count the number of carbons for an organic compound. Then you count, let's just rub that dash out over there. You first find out the number of carbons, and then you find out number of hydrogen. Now they knew that the H to the C ratio for alkanes is greater than 2. So when they found out C6H6, this ratio is 1:1, they expected what? More of double bond and more of triple bond. That is when they eventually realized that there also can be a cyclic possibility. So all of this was actually on observation and possibility. It was not that the first thing they found in benzene was their structure. They looked at the structure and they found out, okay, benzene looks like this. Because they found out a little abnormality between the number of carbons and the number of hydrogens. That is when they realized that things are a little different for this particular structure, and because things are a little different for this particular structure, they'll have to view at it differently. Since double bonds are easily cleaved, what do we mean by cleaved? Cleaved is nothing but broken down by oxidative reagents such as potassium permanganate. What is potassium permanganate? Very important oxidizing agent in chemistry, potassium permanganate. It is KMNO4. I'll just write it over here. Potassium permanganate. And ozone. Ozone is nothing but O3, ozone. And rapidly add bromine and chlorine. These reactions were applied to the aromatic compounds. Surprisingly, products that appeared to retain many of the double bonds were obtained, and these compounds exhibited a higher difference of chemical stability compared to alkenes and cycloalkanes. Very important. So what did they do was, they first found a double bond. When they found a double bond, they wanted to attack the double bond by adding oxidizing reagents. So now when they wanted to attack the double bond by adding the oxidizing reagents, they finally would have thought the expectation for the product was a single bond product. But what eventually happened in reality was, they found a very stable product containing double bonds. This is what has actually happened. So they didn't understand, when they did a reaction to break the double bond and get into a single bond, then why did this double bond still stay? So that is the reason why on treatment with hot permanganate solution, cinnamon aldehyde gave a stable crystalline C7H6O2 compound called as benzoic acid. Benzoic acid looks something like a benzene ring, and on top of a benzene ring you will have COOH attached to it. So this is a benzene ring and you have COOH attached to it. Let me just draw a more clear version of it. This is a benzene ring. This is a C double bond O OH attached to it. This particular thing is known as benzoic acid. Very important. The H to C ratio in benzoic acid is less than 1, again suggesting the presence of several double bonds. Benzoic acid was eventually converted to a stable hydrocarbon benzene. Of course, you can just remove the COOH, get it attached with something else, and you can just have a benzene ring, C6H6, which will prove unreactive to common double bond transformations as shown. Over here, if you can see, you have C6H5 COOH benzoic acid on CaO, and you have 3 different reactions. In presence of H2SO4, it is not giving a reaction. In presence of Br2, it is not giving a reaction. In presence of KMnO4, it is not giving a reaction. But if you see benzene over here, in presence of Br2 and FeBr3, it is giving me bromobenzene. In presence of H2SO4, it is giving me benzene sulfonic acid. So let me just show the reactions to you which are giving me some kind of result, some kind of product. I have benzene over here. Benzene in presence of Br2 plus FeBr3 is going to give me a bromobenzene. Now what exactly is bromobenzene? Bromobenzene is nothing but benzene with Br2 attached on the top of it. Bromobenzene. Similarly, if I have benzene in presence of H2SO4, so this is benzene H2SO4, correct? So what will I do? I'll just show you all how it looks. I can just write HOSO3H, and then I can just attach this over here, making it benzene sulfonic acid. This thing, the product over here was bromobenzene. This is benzene sulfonic acid. The major things to remember over here is whether it is bromobenzene or benzene sulfonic acid, the double bonds inside the benzene were as they were. The double bonds inside the benzene for both reactants and products were as they were. They only added something over here at the top. That means the double That means the double bonds were not breaking apart. As experimental evidence for a wide assortment of compounds was required, those incorporating this exceptionally stable 6-carbon core came to be aromatic. So eventually people said that if I have benzene as my nucleus, that means if I have the 6-carbon ring in the middle, then that particular compound has the possibility of being aromatic in nature. That was what was discovered at that point of time. If benzene is forced to react by increasing the temperature and or by addition of catalyst, it undergoes substitution reaction rather than addition reaction that are typical for alkenes. That means, let me first draw benzene. This benzene is generally not going to react with anything. This benzene is happy and stable as it is. Why? Because it's an aromatic compound. Aromatic compounds are stable in nature. They do not want to react. But if we add different kinds of catalysts, give some heat, some pressure, and give a suitable condition, what will this benzene do is, the carbons stay as they are, the double bonds stay as they are, the H gets substituted by Br. The other H's stay as they are. Generally in alkenes, addition reaction is common, wherein if there is an alkene and something is added, then I'm just giving a random example over here just to make sure people understand. The double bond breaks off and then Br is added. This is addition reaction. But over here in the above example, this is substitution reaction, wherein no bond breaks. There is no breakage of double bond. That means all the double bonds are intact and the hydrogen is substituted, or the hydrogen is replaced. Over here there is bromine. You can have OH, you can have COOH, you can have nitro group, you can have amine group. Different forms are there. That is something which is possible. So it undergoes substitution reaction rather than addition reaction. This further confirms the previous indication that the 6-carbon benzene core is unusually stable to chemical modification. The conceptual contradiction presented by a high degree of unsaturation, which is low H to C ratio, and high chemical stability for benzene and related compounds remain unsolved puzzle for many years. When they saw the molecular formula was good enough. The molecular formula helped people understand that okay, this particular thing is nothing but alkenes. And because this particular thing is alkenes, then there is a possibility of addition reaction and they are not very stable. So according to the molecular formula, when we talked about the molecular formula, they were unstable. But when we talked about the actual participation of that compound into reactions, it came out as very stable. The compound did not act as expected in the reactions. So this particular mystery remained unsolved for many years until people actually discovered how benzene looks like, how it works like, how it behaves. For now it is not a mystery because everyone studies the chapter of aromaticity. Everyone understands aromatic compounds. But before that, it was a mystery. Eventually, the presently accepted structure of a regular hexagonal planar ring of carbons was adopted, and the exceptional thermodynamic and chemical stability of this system was attributed to resonance stability of a conjugated cycle, triene. And this is how the benzene ring looks. It's a benzene ring with alternating pi bonds. These alternating pi bonds keep on moving from the place from which they are to the place besides it. And that is the reason why they got a benzene ring with a circle in the middle stating that the pi bonds are moving. 3 pi bonds, 6 pi electrons. Here, two structurally and energetically equivalent electronic structures for a stable compound are written, but no single structure provides an accurate or even an adequate representation of the true molecule. The six-membered ring in benzene is a perfect hexagon. All carbon-carbon bonds have an identical length of 1.4 angstrom. The cyclotriene contributors would be expected to show alternating bond lengths, the double bonds being shorter than the single bonds. The double bonds are always shorter than the single bonds. So over here, if you see, the double bonds are 1.3 angstrom units long, whereas the single bonds are 1.54 angstrom units long. An alternative representation for benzene is a circle with an hexagon, emphasizes the pi electron delocalization in this molecule and has the advantage of being a single diagram. In such cases, the electron delocalization described by resonance enhances the stability of the molecule, and compounds composed of such molecules often show exceptional stability and related properties. Evidence for the enhanced thermodynamic stability of benzene was obtained from measurements of the heat released when double bond in a 6-carbon ring is dehydrogenated or basically hydrogenated. That means adding hydrogen catalytically to give cyclohexane as a common product. In the diagram, cyclohexane represents low energy reference points. Addition of hydrogen to cyclohexane and releasing the heat to 28.6 kcal per molecule. So what is basically happening over here is, when we have benzene, these are double bonds. Let me just draw the carbons as well. These are the carbons for the double bonds. And these are the hydrogen attachments to it. This is how it looks. Hydrogenating it is addition of hydrogen in such a way that the double bonds break off. This is how a cyclohexane looks with H2. Addition of hydrogen, 2 times the hydrogen of what it was for benzene. This particular thing is hydrogenating it. If we take the value to represent the energy cost of introducing one double bond to 6-carbon ring, we would expect cyclohexadiene to release 57.2 kcal per mole after complete hydrogenation, and 1,3,5 hexatriene, the cyclohexatriene, to release 58.8 kilocalorie per mole. These heats of hydrogenation will reflect the relative thermodynamic stability of the compound. If you can see over here, we can see cyclohexane and we can see energy. Benzene, however, is an extraordinary 36 kilocal per mole, more stable than expected. Benzene is much more stable than cyclohexane. This is much more than expected. People always thought that alkanes were the most stable. After that, in the stability came alkenes and finally alkynes. But after seeing benzene, people were shocked to see 36 kilocal per mole. The molecular orbital description of benzene provides a more satisfying and general treatment of aromaticity. We know that benzene has planar hexagonal structure in which the carbon atoms are sp2 hybridized, and all the carbon-carbon bonds are equal in length. As shown below, the remaining cyclic array of 6p orbitals overlap in general, forming 3 bonding and 3 anti-bonding. The plus and the minus signs which are shown in the diagram do not represent electrostatic charge, but refer to phase the equations. Of course, we have studied the in phase and out of phase, sigma and sigma star bonding and anti-bonding orbitals. When the phases correspond, the orbitals overlap to generate a common region, which is the light phase, with those orbitals having the greatest overlap being lowest in energy. The remaining carbon valence electrons then occupy these molecular orbitals in pair, resulting in a fully occupied set of bonding molecular orbitals. This is how it looks like. If you can see, the orbitals are overlapping. These molecular orbitals over here, if you can see, are overlapped. Correct? So now this is the sigma bond, and these are the overlapping orbitals. Overlapping orbitals show that they are in phase, and then they are trying to form a region of stability. It is this completely filled set of bonding orbitals or closed shells that give the benzene ring its thermodynamic and chemical stability, just as a filled valence shell octet confers stability in the inert gases. Now moving further to pyrrole, many important biomolecules behave as aromatics even though they don't contain benzene. It is not necessary for a particular compound to contain benzene to know whether it is aromatic in nature or not. Aromaticity is not just about the benzene nucleus. For example, right now we have something like this. Let me just draw the structure first so that you all can understand how it looks like. It's a nitrogen. Yes, it's a nitrogen and H attached to it, and double bond over here and double bond. This particular thing is known as pyrrole. Okay, many important biomolecules behave as aromatics even though they don't contain benzene. Histidine is a very common example of amino acid. It's a basics of DNA and RNA. Closer examination shows that these compounds follow Huckel's rule. We'll see for pyrrole, and the variations involve the inclusion of lone pair and pi bonding system. So as we have seen the structure of pyrrole, we understand that pyrrole is a 5-membered ring with a nitrogen in it. It contains 2 carbon-to-carbon double bonds. We can actually draw the structure of pyrrole over here. And then what we can do is, at this point of time over here, we can have N in the middle. So it looks like a 5-membered ring. The last carbon is replaced by nitrogen, H, double bond here and double bond here. So you can also call it as a 4-membered ring as well. If you look over here, let us just fill in the hydrogens. This nitrogen has a lone pair. Is this particular structure cyclic in nature? Yes, it is cyclic in nature. Is it conjugated in nature? Let us see that. You have sigma, pi, sigma, lone pair, sigma, pi. So it is sigma, pi, sigma, lone pair, sigma, pi. Remember, instead of a lone pair, you can have a pi. Instead of a pi, you can have a lone pair. That means over here, this can be considered as pi. Why am I saying so? Because pi is nothing but 2 electrons, even lone pair is nothing but 2 electrons. So for your convenience, you can consider. If you do not want to consider, you cannot consider. But while considering it, if it becomes a benzene ring, that means it becomes an aromatic structural ring, then we should consider. We will look into it. First, let us see cyclic is there, conjugated is there. Of course, we have to consider every compound as planar compound, so even that is there. No issues with that as well. So 3 things are in place. And because all of these 3 things are in place, we have to go and find out for a Huckel's rule. Huckel's rule says 4n plus 2, which is 4 into 1 plus 2, which is equal to 6. So this particular thing should have 6 electrons. Let us see. 1, 2, 3, 4 of the lone pair, 5, 6 over here. So thus we can see that pyrrole is aromatic in nature. It usually reacts in a way similar to benzene rather than alkanes. But how does it fit into the rule of aromaticity? It is cyclic, it is flat means planar, it is conjugated, it does have a double bond, single bond, double bond, lone pair. We have seen before the lone pairs can be conjugated with pi bonds. So lone pairs can be considered as a pi bond. So pyrrole is conjugated all the way around the ring, counting the lone pair as a part of pi electrons, giving it an odd number. The lone pair can act as a pair of pi electrons if the molecule will become aromatic as a result. That's a very important line. If using a lone pair, the particular compound becomes aromatic in nature, use it. If it does not become aromatic in nature, then leave it. Does a lone pair always have to act as a pi pair? No. So over here they have given the example of pyridine, and pyridine is exactly same as benzene. And when you do pyridine, there is a lone pair in pyridine as well. But at that point of time, you do not need the double bond. Then you should not use it. So for example, let me just draw pyridine over here for us to understand it. I have N over here. I have double bonds like this. So if you see 1, 2, 3, 4, 5, 6. 6 pi electrons have been found only by the pi bonds. Then we do not need the double bonds anymore. We do not need the lone pair anymore. So we will not use this particular lone pair at all. We use lone pairs only where it is needed. We do not use lone pairs where it is not needed. Very important for us to understand. The nitrogen has lone pair. Tellurine already has 3 pi bonds. It is flat, fully conjugated. So if I include these 2 electrons, it becomes 8 electrons, which is anti-aromatic. We do not want a compound to be anti-aromatic in nature, so we will not use it. The compounds itself do not use it and stay aromatic. There is already pi bond on that nitrogen, so it would be difficult for the lone pair to occupy the same space above and below the ring. Instead, the lone pair remains orthogonal to the pi system. It is the plane of the ring rather than above and below of it, and completely avoids the interacting with the pi system. A lone pair can act like a pair of pi electrons if there is already another pair present. So with this, we see the history behind the structures of benzene and pyrrole. We see the structures itself in detail. And finally, we also see the bonding of it. Thank you so much for watching this Thank you so much for watching this video. Stay tuned. Thank you.